Hello and welcome to section 3.11. We are going to look at chemical equations some more, and we're going to look at interpreting them. We're going to talk about something called mole-to-mole ratio. So first, let's just look at something that you're very familiar with, because moles are a little bit abstract. We're going to talk about making a sandwich. This is kind of a gross sandwich with this fake American cheese, but it makes a really nice example. Let's say you want to make a sandwich and you have 2 slices of bread, 1 slice of cheese, and voila, there's your sandwich. So we know that it takes 2 slices of bread and 1 slice of cheese to make that one sandwich. We could talk about this in a different way too. We could say, well, we could have 2 dozen slices of bread and 1 dozen slices of cheese, and we could make 1 dozen sandwiches. So there are different ways that you could interpret that. Let's look at this when we apply it to chemical situations. Let's look at a balanced chemical equation here. We have the synthesis of hydrogen and oxygen to make water. We could look at this in a similar way. We have 2 hydrogen molecules, 1 oxygen molecule, and we get 2 water molecules. We could look at it that way. We could look at individual atoms or molecules. We could look at dozens of atoms or molecules. We could say if we start with 2 dozen hydrogen molecules and 1 dozen oxygen molecules, we get 2 dozen water molecules. We could do the same. That makes sense. That's true. It's correct. We could also do this by looking at the number of moles. Remember, a mole is simply 6.022 times 10 to the 23rd atoms or molecules. Just like 1 dozen is 12, 1 mole is this many, okay, pieces. So we could talk about it in terms of moles as well. We can say 2 moles of hydrogen molecules plus 1 mole of oxygen molecules gives us 2 moles of water molecules. So here's a little problem for you. How many molecules of water are produced in the following reaction? And also, how many moles of water? So here's our reaction. We have nitrogen monoxide, hydrogen, nitrogen gas, and water as a vapor. So how many molecules of water are produced? Well, we know that there are 2 water molecules in this reaction. How many moles of water? 2. There would be 2 moles of water produced. So here is our answer restated. When we look at chemical equations, we most often talk about them in terms of moles. When you're balancing your equation, you're looking at the individual atoms and individual pieces, but as we step back and look at the overall equation, moles are very, very useful in helping us understand ratios. And we're going to talk about this mole-to-mole relationship further here. The coefficients of a balanced chemical equation represent the mole ratios of the reactants and the products. In order for this to be true, the equation must be balanced, absolutely must. So let's look at an example right here. We have a balanced chemical equation. It's the same one from up here. We have an unbalanced chemical equation. If our equation is unbalanced, it always looks like the chemicals react in a 1-to-1 ratio. In this unbalanced chemical equation, we just have 1 of these molecules and 1 of these produce 1 of these and 1 of these. And that isn't true. Remember our sandwich. We have 2 slices of bread for every sandwich, right? Well, in a similar way, there are different ratios that are going on with our equation, and we have to have a balanced equation so that we can see what those ratios are. Okay, now let's look, now that we understand this mole-to-mole relationship in a chemical equation, let's look at an example. Let's say we have 4 moles of water in this decomposition reaction. We're taking water and breaking it down into hydrogen and oxygen, and we start with 4 moles of the water. How many moles of oxygen will we get? Well, we know our mole-to-mole relationship in this. Let's take a look at that. We know we have 4 moles of water, and we want to know how many moles of oxygen, right? Well, we know from our equation that 2 moles of water is going to produce 1 mole of oxygen. So when we set up our wonder fraction, our great big fraction, okay, we're going to start with 4 moles of water, and we're going to multiply by this conversion factor. 2 moles of water, and we want this on the bottom so that the moles of water cancel out, equal to our 1 mole of oxygen. Okay, so here is our ratio, our conversion factor right here, just restated. I put the moles of water on the bottom so that those would cancel out. The moles of water cancel out, and I am simply left with 4 divided by 2 moles of oxygen, which is going to be 2 moles of oxygen. So if I start with 4 moles of water, I can produce 2 moles of oxygen. This is very simple because you could simply look at this and probably do that in your head. But I would like you to get used to writing this out so that when the problems get more complicated, you'll be able to do them. So now you try. Go ahead and pause the video, and if you start with 5, that's supposed to be 5.0 moles of water, how many moles of oxygen will be produced? So we're going to do this the same way. We're going to start with our 5 moles of water. It's what we know, right? We start with 5 moles of 5.0 moles of water. How many moles of oxygen will be produced now? Well, let's multiply by our mole to mole ratio. Remember from up above, 1 mole of oxygen is equal to 2 moles of water. Our moles of water cancel out, and we have 5 times 1 is 5, and on the bottom we only have a 2. So it's going to be 5 divided by 2, it'll be moles of oxygen, and that's going to be 2.5 moles of oxygen, and that's our answer. Now here is another type of problem. It's really not any different, but it's asking us to calculate the number of moles of oxygen required to react exactly with 4.30 moles of propane. So rather than saying we have so much propane, how much CO2 is it producing, we're going to be asking a different question. We're going to say if we have 4.30 moles of propane, how many moles of this oxygen do we need to make this an exact reaction so they react evenly? So we're going to do this in a very similar way. We're going to start with what we know. 4.30 moles of propane, we know that. And we want to find the moles of oxygen. So if we start with 4.30 moles of propane, we're going to need to multiply by our conversion unit, our equivalence statement, right? Our mole to mole ratio. I'm referring to the same thing by all 3 of those terms. What is our mole to mole ratio between oxygen and propane? We know that 1 mole of propane is equal, we have 1 mole of propane, is going to be equal to 5 moles of oxygen. So we're going to use this equivalent statement right here in our big fraction, okay? We want moles of propane on the bottom so that they cancel out, and our 5 moles of oxygen on the top. And when we do the math, we are in essence saying 4.30 times 5, that will be our numerator, and 1 is on the bottom. Moles of propane cancel out, and the answer is 21.5 moles of oxygen. And we only use, for just a little review here, 3 significant figures in our answer because we're limited by 3 significant figures here. these are exact numbers, so we don't need to be limited by these numbers. We know then that if we're given 4.30 moles of propane, we have to have 21.5 moles of oxygen in order for the ratios to work out evenly. Okay, here is another example. If you would like to pause the video right now, go ahead and pause it, and you can work this out on your own, see if you can get the right answer, and then turn the video back on and check it. And I will put the answer on this page. Okay, here is the answer to this example. We know that ammonia, NH3, is used in huge quantities as a fertilizer. It's looks like I forgot to capitalize the I there. It is manufactured by combining nitrogen and hydrogen gases according to this equation. 1 molecule of nitrogen, 3 of hydrogen, and 2 yields 2 ammonia. 2 moles of ammonia. So we know our mole-to-mole ratios here, 1 to 3 to 2. They're asking us to calculate the number of moles of ammonia that can be made from 1.30 moles of hydrogen gas reacting with excess nitrogen. That means they're giving us plenty of nitrogen. We don't need to worry about how much nitrogen is there. We just need to worry about the hydrogen. So, if we start with our 1.3 moles of hydrogen, we want to know how many moles of ammonia can be produced as a product. Start with our 1.30 moles of hydrogen. We also know that our mole-to-mole ratio here is 3 moles of hydrogen. It's going to give us 2 moles of ammonia. So we can use this as our conversion factor, as our mole-to-mole ratio, as our equivalence statement. And let's go ahead and write that in to our big equation here. Okay, 1.3 moles of hydrogen on top, so we want to put the moles of hydrogen on the bottom. 3 moles of hydrogen for our ratio to 2 moles of ammonia. So we continue calculating. Our moles of hydrogen cancel out, and we get, we will say 1.30 times 2 for the numerator, and our denominator will just simply be a 3. And when we do the math, we get 0.867 moles of ammonia. And that is our answer. Just a reminder, we have 3 sig figs here. We're limited by these 3 sig figs. These are exact numbers, so we don't need to worry about those being limiting. So we just answered the question. If we start with 1.30 moles of hydrogen and plenty of nitrogen, we can produce 0.867 moles of ammonia in our equation. So I look forward to seeing you in class and helping you solve some more of these problems.